So first things first, we talked in the last video about signed versus unsigned integers, right? We talked about unsigned integers and we talked about 2's complement signed integers. So how do we go back and forth between them? Well, the good news is this is actually really simple. The basic idea is you just keep the same bit representation and reinterpret. So we can visualize it through the functions that we've talked about a little bit. So if I take a 2's complement integer x, I can actually run it through a function that we'll call t to u, so 2's complement to unsigned. And that would actually be comprised of two of the functions we've talked about. We would go from 2's complement to the bit representation, and then from the bit representation to unsigned, and out of the other side pops the unsigned integer. But again, all we're really doing is keep the bit representation. We don't have to do an actual operation here. We just reinterpret what we already have. The same thing works going from unsigned to 2's complement. We create a new function here, a new box called u to t, or unsigned to 2's complement, where we'll go from the unsigned to the bit representation, then from the bit representation to the 2's complement value. But again, we're just keeping the exact same bits and reinterpreting them based on what we need. And this is how we do things with everything in computer systems, right? Everything is just a bunch of ones and zeros, and yet this turns into all the incredible graphics and computational power that we have these days because we are completely free to interpret our data however we need to interpret it. And this is a shining example of that, right? I have a bunch of bits. If I need them to be unsigned, then that's how I'll interpret them. If I need to switch from that to a 2's complement, then I'm just going to keep the same data, interpret it slightly differently. So this makes mapping between signed and unsigned really, really easy, right? We never have to actually go in and modify any of the bits. As we saw in the last video, signed versus unsigned, the bit representations pretty much stay the same. So if I want to convert from a -8 signed, I still just keep the bit pattern 1000. In unsigned, that just translates to 8. -7, 1001 just translates. If I just interpret that as unsigned, it becomes a 9. I don't really have to do anything. And as we saw also in the last video, notice that until we get some weight in that most significant bit, everything actually matches up. Signed and unsigned have the same representations until we end up with a 1 in the most significant bit of our representation. So let's take a moment and take a look at why that is. Now, when we're looking at a bit pattern and figuring out what it represents, either in unsigned or signed, it works almost entirely the same way. The only difference is in that most significant bit, and that's where the change comes in, right? And if we think back to those summations that we saw in the last video, we see where that happens. We go from 0 to w-1 with unsigned, and we just add up the weights of the bits that have a 1 in them. Now, with signed, with 2's complement, we do the same thing, but remember in the 2's complement function, we actually had the w-1 bit broken out and it had a negative weight. That's the only difference. A large negative weight in 2's complement becomes a large positive weight in unsigned, and vice versa. If we go from an unsigned, we take that most significant bit that would have a large positive weight, it just becomes a large negative weight when we're dealing with 2's complement. So it's a very simple thing. It's the only thing we have to remember. If it's 2's complement, when you figure out what the weight of that most significant bit is, just make it negative. Now, obviously, if there's a 0 in the most significant bit, it doesn't matter, and the unsigned and 2's complement are going to have the same values for the same representation. If there's a 1 in that most significant bit, for 2's complement, we just subtract that weight instead of adding it as we do in unsigned. Now, to visualize that, we can see that from 0 to t max, Again, same representation has the same value. It's when we actually get into the negative numbers. It's when the 2's complement becomes negative that we get into a different range. The 2's complement range is just shifted down a bit from the unsigned range because we have to deal with the negative numbers. So those negative values, if you have a negative 2's complement value, that translates to a higher unsigned value, right? That's the stuff that's going to be up in the top of the unsigned range. And this graphic just shows you how certain things kind of relate to each other, so you can get an idea of what you're looking at. A -1 is 2's complement is going to be equal to unsigned max. Then as we go to -2, it's unsigned max -1, and that works 1-to-1 all the way down until we find that T min ends up being equal on the unsigned to T max plus 1. So this gives you an idea of how these things relate, and this is a handy thing to know. It's a handy thing to keep that in mind because converting between 2's complement and unsigned is something that happens fairly often when you're programming. So it's a good idea to have this graphic kind of in the back of your head so that you have an intuitive understanding of what's going on when you're doing these conversions. So now that we've talked about the idea of going from signed to unsigned and back, let's talk about what we actually see, how this actually works when we're doing it in C. Now, something to keep in mind for constants is that by default, they're considered to be signed, and we have to add a U, capital U, as a suffix if we want it to be unsigned, and there's a couple examples right here. So if we just declared these without the U suffix, those would be considered to be 2's complement. On the other hand, putting the U on makes them unsigned. Now, explicit casting between signed and unsigned works the same as those functions we talked about, our unsigned to 2's complement and 2's complement to unsigned functions. So we can see a little code snippet here where we just cast, just like we've seen in various other languages. We can directly cast from an unsigned to a 2's complement or the other way around just by putting in these keywords in these parentheses before the variable itself. So this is how we do an explicit cast. That's pretty straightforward. But we also have implicit casting. Now that occurs in assignments and procedure calls. But here's a question, which way does it go? If I assign unsigned to a signed variable, if I assign a signed value to an unsigned variable, which way does casting go, right? How does that happen? So let's take a look at that in the next slide and make sure that we don't get too surprised by how this works. So let's talk about how casting works and take a look at some examples, some of which are going to work exactly as we would think, and some of them might have some surprising results. So the first thing to keep in mind is we have some rules. If there's a mix of unsigned and signed in a single expression, then the signed values are implicitly cast to unsigned. So that's the thing to remember. If we mix up our signed and unsigned, then everything gets cast to unsigned. This includes comparisons. And that's where we can get some kind of weird results. And it's great for examples, so let's walk through these. Now, these examples are going to be for a word size of 32. And we've got our T min and T max here, so we can kind of keep track of what those are, because that's going to matter. Because remember, when we start talking about the difference between signed and unsigned, these T min and T max kind of set our boundaries. They tell us where things start getting a little weird. So if we go from just compare a signed 0 to an unsigned 0, and we see if those are equivalent, well, okay, they are equal, but they're going to both be evaluated as unsigned, and that's not surprising, right? That's the start of our range where signed and unsigned start becoming equivalent to each other. So that's not surprising as far as the result goes, right? They're going to evaluate to being equal to each other, but the evaluation is going to be done as unsigned. So constant 1 is going to get implicitly cast to unsigned. Now, if we have -1 and 0, -1 evaluates as less than 0. Those are both signed values, because remember our other rule, we have to have that U as a suffix if we want something to be unsigned. So that one's not surprising either. Now we start getting into some other stuff. A -1 for constant 1 and an unsigned 0 for constant 2, that -1 is actually going to evaluate as being greater than 0 because remember, we've mixed our values, right? We've mixed a signed with an unsigned, which means it implicitly gets cast to an unsigned. And when we take a -2's complement value and cast it over to unsigned, it becomes positive. We keep the same bit pattern, but it ends up being positive. It actually ends up being U max. So with that one, you might not notice this in code, right? It can be a little weird to keep track of what kind of variables you have, but this is the kind of thing that makes it so important so that a -1 doesn't end up being evaluated as being greater than a 0. Our next example, we have two signed values here, right? And so we have T max, and then we're comparing that to basically T min, right? That's going to come up being greater, and it'll be evaluated as signed because both values are 2's complement, so that's no surprise. However, if we have that first one, if we have the T max value in constant 1, if we have that declared as unsigned, then both get cast over to a signed value, and that's actually going to end up being less than T min minus 1 because, again, that's going to get cast to a positive value. It's going to get cast to unsigned, and so that large negative weight becomes a large positive weight, and constant 2 ends up being larger than constant 1. So that's another one that can be a little odd. -1 is greater than -2 when both are signed. No surprise there. An unsigned -1, however, if we cast -1 to unsigned, then the -2 implicitly gets cast to unsigned. So we still end up with the same evaluation, right? The relation, it's still greater than, but it's actually evaluated as an unsigned instead of a signed. So this is another thing to be very careful of. Just because you actually end up with the correct evaluation of the relationship doesn't mean that something maybe surprising isn't happening, right? We've actually converted both of these. We've cast both of these to unsigned values, and they end up still being greater than, but it's done as an unsigned instead of a signed, so we have to watch out for this. If we compare T max to basically T max plus 1, but unsigned, then that gets evaluated as unsigned, and that works pretty much the way we would expect it to. Although keep in mind that if we tried to do that constant 2 value as a 2's complement, it would do weird things. It would end up wrapping around on us and becoming a negative value. Now, finally, with this last one, we actually have a couple things going on. We've got a mixture, but we're actually going to implicitly cast an unsigned value in constant 2 to a 2's complement value, which ends up flipping that thing negative, right? That's greater than T max, and that means that it ends up and evaluating as a negative number. T max plus 1 actually ends up being T min. So because of that, we've got what looks like constant 1 should be less than constant 2. And it's not a surprise that it evaluates as signed, but because of that conversion from a number that's outside of the 2's complement range for a 32-bit word size, it ends up evaluating as greater than. So this shows you, again, some things that are exactly as we'd expect and some things that look a little odd and are, in a lot of cases, easy to miss when we're coding. We have to be sure to be very, very careful about mixing 2's complement and unsigned because it might end up doing things that we are not expecting, and that's never a good thing when you're programming. So to summarize, when we're casting between signed and unsigned in either direction, we've got some basic rules that we want to keep in mind. We always maintain our bit pattern. We're not actually, when we're just going between signed and unsigned, we're not going to actually change the bits at all. We're just going to reinterpret them. We can have unexpected effects, right? If we're adding or subtracting 2 to the W, if we start getting pretty close to our maximums or minimums, things can start doing odd things. We can get into things like overflow and wraparound that will talk a little more deeply about in future videos. And the big one to keep in mind, because this leads to so much confusion, expressions containing signed and unsigned integers always going to have the signed integer implicitly cast to unsigned. So keep that firmly in mind and look out for that. That's something that causes a lot of very strange looking behavior in programs until you get used to thinking in those terms. Now, beyond simply converting between signed and unsigned, we might actually have to make things larger or smaller. We might have a change in the number of bits that we're going to use to represent a value. So what do we do in that case? Well, let's start with extension, right? Let's start with going to a bigger representation, because that one's actually pretty straightforward. With unsigned, it's easy, right? We just add a bunch of zeros to the most after the most significant bit. So if we make a larger representation, we think of it as expanding to the left, and we just add a bunch of zeros because it's all going to work the same way. We want to keep the same value. We already have that value in our smaller representation. We just add a bunch of more significant zeros, and we land on the same value. So for unsigned, it's very, very simple. Now with signed integers, it's a little more complicated, but not by much. It's actually a very, very simple process. So to convert a given W-bit signed integer to a W plus K bit signed integer, right? If we're going to expand it by K digits, all we have to do is something called sign extension. And that just means we make K copies of the sign bit and fill those to the left. So what we'll end up with is just a bunch of copies of the most significant bit that's already there in the smaller representation. So let's take a look at a couple examples to make sure that that's clear. So here we see we've got ourselves some shorts that we've declared in this code snippet, and we're going to expand them to full integers. Well, easy enough. If we've got this top representation here, we've got 16 bits. We're going to expand that to 32 bits. We're going to go from a 2-byte short to a 4-byte int. All we have to do is make a bunch of copies of the most significant bit and tack them on the left. So for 15,213, our most significant bit is 0, so we just add a bunch of zeros. We end up with the same value. The same thing applies if we've got that negative 15,213. We're just going to look and see, my most significant bit is 1, so I'm going to just extend to the left by, in this example, it's going to be 16 bits, and we're just going to copy that most significant bit every single time. We just add them all up. And when we think about how 2's complement works, that makes a ton of sense, right? We have in our 16-bit representation, that 1 has a large negative weight. When I move it to a larger representation, that 1 that's already there is actually going to switch over to a positive weight. So we're going to add a bunch more positive weight because our most significant bit in the 32-bit representation has a much, much, much bigger negative weight. So we've just got to offset that. And this works by simply replicating that most significant bit all the way out for the however far we're extending. So the expanding and truncating really is very straightforward. So once again, we have some basic rules that we want to keep in mind when we're expanding. So say going from a short integer to an integer. For unsigned, we just add zeros, right? We just add zeros to the left. For signed, we do sign extension. So that just means instead of just adding zeros, we just replicate the most significant bit. So if it's already a 0 in the most significant bit, we just add zeros. If it's a 1, we add 1s. And both of those will yield the expected result. Now, truncating, it's not much more complicated. It's basically just going to do a modulo. It's going to do a mod operation. So for both signed and unsigned, this is easy. The bits are just truncated. So if we were going from a 32-bit to a 16-bit and we're truncating, we just chop off the most significant 16 bits and reinterpret the result. So for expansion, we're going to land at the same value, but for truncation, we're actually going to change the value potentially. Now, if I already had just a bunch of zeros, and I have a 0 left in my most significant digit, then we're still going to end up with the same result. However, if we're cutting off anything that's got some weight to it, or if we're cutting off the 16 and what's left after we truncate, we go from having a 0 in the most significant bit of the 32-bit representation to having a 1 in the most significant bit of the 16-bit representation, then we're actually going to flip the sign, right? It's going to work a little differently. So it's kind of going to be similar to a mod operation, but it might actually flip the sign on us, for example. But for small numbers, this yields expected behavior as well. For small enough numbers, they're not going to change. The actual evaluation won't change. Once you get to a large enough number where you've actually got some weight in the part that you're truncating, for unsigned, you'll be doing a mod, and for signed, it's similar to a mod, but you may even be flipping the signs around. So these are things to keep watch on, and if you go through and kind of do some examples yourself, you'll find out that this is all very predictable.